Up until this point, we've been talking about forces that are acting on a single point. So you might have multiple forces that are acting on a single object, but because they're all acting at the same point, they can be resolved into one single vector that'll cause one translation from one place to another. So this might be your object here. All the forces that are on it will net out to one thing, and that resultant, whatever that force resultant is, the motion will be in that direction too. It'll be accelerated in that direction, whatever that net force is. However, it's possible that instead of having forces at only one point, you have forces at multiple points on the object. Like this would be an example. This happens all the time. What would happen if you had an example like this, where the forces are at different spots, is instead of just translating, instead of just moving in one direction, the thing is also going to have a tendency to spin. Let's take a look at that. Two parallel forces acting at different points are going to produce rotation. So let's imagine this. Imagine that I've got this object here, some random object, and I've got forces like this acting on this object. Well, that's going to tend to make this thing want to rotate, like so. So the thing is spinning around here because of the fact that the forces that are acting on it are not acting on the same point. So how do we deal with that? Well, there's a concept that goes along with this idea that helps us, a tool that helps us to understand this and to make predictions about it. It's called torque. Torque is a measure of the propensity for that kind of rotation. So it's a way to deal with forces that are not all at the same point. Torque is an analog. You can think about it as the rotational equivalent of force. So force makes things move in a straight line. Torque makes things rotate. Here's how we define torque formally. Torque, which is abbreviated with, here it looks like a T. It's really supposed to be the Greek letter tau, capital tau. The lever arm is just the length between the center of pivoting, or the center of rotation for this object, and where the force is applied. Here's an example. Here's a beam or something like that. It pivots obviously at this point. Often it's very easy to tell where the pivot point is going to be. It's got to pivot there. And there's a torque that acts on this object in the clockwise direction. Clockwise means the way a clock normally runs, so it'd be that way. Well, it's this force, this 600 Newton force, would cause this thing to rotate in that direction. And the lever arm here, the distance between the pivot point and where the force is applied, is a half a meter. So we take that 600 newtons, the force, times the lever arm, the half meter, and it comes up with a torque. You notice that the units on torque are force times distance, so it would be Newton meters. In the English system, the traditional U.S. units is pound feet, but it's often said backwards, foot pounds. And if you're into cars and trucks and motors, you probably have heard foot pounds being thrown around as a measure of torque before. Well, you try this one. What's the counterclockwise torque on the seesaw? Stop the video and give it a try. Okay, we can solve for this the same exact way, just by using the definition of torque. So the torque counterclockwise here is going to be whatever force on here that would cause counterclockwise rotation. Counterclockwise, of course, means opposite the direction a clock would normally run. So the force that would do that would be this 500 Newton force. So that's F in my equation, and I have to multiply that by lever arm. Well, the lever arm is, once again, like in the last problem, 0.5 meters, because that's the distance between where the force is applied and where the pivot has to be. So 500 times 0.5 is 250, so that means that we have a 250 Newton meter torque, counterclockwise direction. Okay, there are net torques just like there are net forces. So to find the net torque, we can, if we take clockwise as the positive direction, so we're just going to assume that that's plus, what's the net torque on the seesaw? Well, we found out that the clockwise torque in our first problem was 300 Newton meters, and we found out in the last problem that our counterclockwise torque was 250 Newton meters. So that's negative because it's counterclockwise, so we subtract 250 Newton meters, and that means that our net torque is 50 Newton meters clockwise. The question here is, what direction of rotation would this torque tend to cause? Well, when we're talking about translation motion, F net equals ma is the equation, and we know that there's a correspondence between the direction of net force and the direction of acceleration, and that is they are the same. Whatever direction the net force is in, that's how the object is going to be accelerated. And the same thing is true for torque. We're looking at the net torque. If that's counterclockwise, well then the object will rotate counterclockwise. If it's clockwise, it'll rotate clockwise. Just like when F net is 0, there's no acceleration. When torque net is 0, there's no change in the state of rotational motion. In other words, there's no angular acceleration. Take a look at this example. What torque is generated here by the 600 Newton force? Well, if you guessed nothing, you're right. Because if you take a look at the lever arm here, since this 600 Newton force goes directly through the pivot point, the lever arm is equal to 0. So even though there's 600 newtons of force there, there is no torque because that force is not acting perpendicular to the lever arm. All it's going to do really is just compress the beam. So the only components of a force that produce torque are components that are perpendicular to the lever arm. So if you have a force that isn't either perpendicular or parallel to the arm, that means it's going to produce some torque, but not all of its force will produce torque. Like here's an example. Let's find the torque that's imparted by the 600 Newton force in this drawing. Well, in order to know that, we'd have to know what part of this 600 Newton force is acting perpendicular to the beam. So we can resolve this 600 Newton force into two components. Imagine this. If I extend this up here like this, I could probably figure out what these angles are. Let's look at it over here. Here's my 600 Newton force. There's this angle for this extended beam. I know from the problem that this is 30 degrees. So if I were to make my horizontal again, this would have to be 30 degrees, but the 600 Newton force is vertical because it's acting by gravity. So this is a 90-degree angle between here and the force. So that makes this is 60. So the component that would be perpendicular to the lever arm is going to be 30 degrees from the net force. Well, that's adjacent to the 30 degrees, and so that means that our torque-producing component, I'll call it force torque, that's going to be equal to 600 newtons times the cosine of 30 degrees. And if you calculate that, 600 newtons times the cosine of 30 degrees, you come up with 520 newtons. So that's the torque-producing force. But I wanted to know the torque, and torque, remember, is force times lever arm. So here it's going to be 520 newtons times the lever arm is a half meter. And so I end up having a 260 Newton meter torque caused by this force. You find this one. Find the torque imparted by the 500 Newton force in this drawing. Okay, here's how you can do this. It's a very similar problem to the last problem. We need to find what component of this 500 Newton force is actually acting perpendicular to the lever arm and therefore will produce torque. Once again, you can reason out that this is going to be a 30-degree angle, and so the torque producing component is going to be 500 newtons times the cosine of 30 degrees. And when you calculate 500 newtons times the cosine of 30 degrees, you come up with 433 newtons. And so the torque, therefore, is going to be equal to 433 newtons times a lever arm, again, of a half meter. And that gives you a 217 Newton meter torque. So our object here is to find the net torque on the object shown in the drawing above. Let's, just so we understand what we're talking about, consider that clockwise is going to be positive here. The first problem told us that we had a clockwise torque that was equal to 260 Newton meters. So that's positive. But this force here is going to tend to make a counterclockwise rotation. So that means negative 217 Newton meters. So the difference between these two, which is 43 Newton meters, is the net torque, and its direction is going to be in the clockwise direction because clockwise was larger than counterclockwise. A concept that's closely related to torque and that you can understand once you understand what torque is called center of mass or center of gravity. Both mean the same thing. And the idea is it's that one point at which all the weight or all the mass could be considered to be concentrated for an object. So I got some some blob here, there is some point in any blob, we call it the center of gravity, where if we were to collapse the whole blob into one spot, that's where the force would be applied. That's where the gravity would be. We usually designate that with this symbol that looks like a circle with a cross inside of it, and the two opposite quadrants are sketched in. Here's another way of thinking about this. This is kind of a working definition. It's the point of application, the center of mass is the point of application of a lifting force that produces no rotation. In other words, if I were to lift here, if I had a stick, like a meter stick or something, and I were to try and lift it up off the table by pushing here, what would happen is it would rotate. By the same token, if I were to try and lift that same stick by pushing up on it over here, it would rotate, but it would rotate in the opposite direction, counterclockwise. But if I took this meter stick and I lifted right there, right in the very middle, for a uniform stick like a meter stick, well, that would only cause translation. It wouldn't rotate. If I could pick it up right at the 50 centimeter mark exactly, I shouldn't see it rotate at all. I should see it only translate. That point is the center of mass. So something like a meter stick that we were talking about in the last example, or a beam or something like that, if it has a uniform shape and its density is uniform, in other words, it's made of the same material all the way throughout, the center of gravity is just the geometric center of the object. So if you have a square bar of steel, this square bar of steel has a midpoint along this axis, and it's got a midpoint along this axis, and it has a midpoint along the other axis too. So that means right at the intersection of those axes, well, there's my center of gravity. All the mass can be considered concentrated there, which makes it easy to solve problems that have these large bars of steel. Any uniform object, like a square bar or round bar or block, something like that, that doesn't have change in shape or change in density, is always going to have at its geometric center also its center of gravity. If the object isn't simple, if it has changing shape or changing density, then the center of gravity is harder to determine. You can determine it theoretically by using some advanced mathematics. Sometimes geometry is enough, but often you need the methods of calculus to do that. Other than doing it with geometry or calculus, you can also, if you have a flat object, use a measurement technique to actually find this. Here's how it works. The first thing you do is just pick 2 points on the object, any 2 points, it doesn't matter. I've labeled them A and B here. First of all, you suspend the object along with a weight from one of the points, and what will happen is the object will swing, like here we saw the object swing down this way, and the weight will hang straight down towards the center of the earth. Well, you mark that line. Just draw a mark there on that line that goes towards the center of the earth. Then move to your other point and do the same thing. You hang your line from point B here, and your plumb bob goes straight down, and the object rotates down so that it's hanging straight down. So you redraw that line. Well, where those two lines intersect, right there, that is your center of gravity for this object. And what's weird is sometimes you can have things whose center of gravity isn't even part of the object. Here would be an example, a donut. The center of gravity of a donut is right there. So all the mass of a donut, if it could be collapsed into one spot, is in a place where there actually is no donut at all. It's a little weird, and for odder shaped objects it even seems weirder, but it works.